So this will be the, we have six short presentation, around 10 minutes each. So let me share, let me introduce people in groups of three. Um, so these are the three short presentation. First, we'll start with Qatar. Safi Khorasani, she is a fourth year PhD student and working with the MVAPICH group. She currently works on the MVAPICH GDR project, and our research interest lies in the HPC and GPU communication and compute. And she will be talking about the performance of ROCm-aware MVAPICH GDR on the Livermore Corona cluster with AMD GPUs. I showed some initial slides in my talk, but she will go into more details, and all the supports, whatever she will be talking, is already available in the MVAPICH GDR release, which we made last week. The second presentation will be done by Chinghua Zhao. He's a PhD student also in the MVAPICH group. He will be talking about performance benefits of the on-the-fly compression on GPU to GPU communication. Once again, I showed some high-level results. He will go into more details. The third presentation will be done by Chen Chun Chen. He's a second-year PhD student, also working on the MVAPICH GDR project. His research interests include HPC and GPU communication. So his talk will be more focused on the performance of MVAPICH GDR on the DGX2 A100 system. So once again, I showed some initial tuned results. He will be able to go into many more details of the results on the DGX2. So maybe Qatar, we can get started with you.
Yes.
You can share the slides.
All right, is that good?
Yes, yes. Please proceed. Yeah.
Okay, so hi everyone. Thanks for the introduction, Dr. Panda. And just to add a bit to the introduction to the talk that you gave, if anyone was present at MUG 2020 last year, we first gave a presentation about preliminary work we were doing on AMD GPUs. And since then, we have made 2 releases with support for MVAPICH GDR on AMD GPUs. So today we're going to present the work we've been doing, and we'll do that through showing the performance of ROCm-aware MVAPICH GDR on the Corona cluster at Lawrence Livermore National Lab with AMD GPUs. All right, so a quick introduction into the work. So GPU-aware Mpi libraries have been the driving force behind scaling high-performance computing applications on GPU systems. And this realm has been heavily dominated by NVIDIA GPUs and the CUDA software stack. And with upcoming HPC deployments like Frontier and El Capitan deploying AMD GPUs, it becomes more important to have high performance with a ROCm-aware MPI runtime as well. So ROCm stands for Radeon Open Compute, and it's the platform used on AMD GPUs. And this work is driven by the need for support of high performance communication stacks with AMD. And we refer to this as ROCm-aware MPI. And there's a lot more detailed information about the work in this paper over here. So for a quick background, Radeon Open Compute, or ROCm, is an open source software platform for HPC and machine learning on AMD GPUs. It has various tools for development on GPUs, APIs, and the drivers that support AMD GPUs. And it also has support for different programming models. And then recently as well, it's been supported in different applications too, such as NemD, GrowMax, ROC HPCG, and a lot more. And you can find the link to the ROCm platform over here. And similar to the way we say CUDA-aware MPI, where CUDA-aware MPI has support on NVIDIA GPUs, we refer to this as ROCm-aware MPI on AMD GPUs. And a quick overview of how ROCm-aware MVAPICH GDR looks like through this diagram. You have the scientific and deep learning applications at the top layer, and then within your MPI runtime, you have your various communication operations, your different protocols, and within this unified device abstraction interface, which we refer to as UDI, you have your different designs and what's supported through the driver or the runtime. And typically, this would have just been over CUDA APIs and NVIDIA GPUs, but in order to avoid duplication of efforts and to not have to make major changes to your code to support new APIs, we now support ROCm APIs at this layer through HIP, and that allows you to run over NVIDIA GPUs or AMD GPUs with MVAPICH GDR. So this design would make it easier to interface with vendor-specific backend implementations. And again, several details of this work were presented at ISC 21 earlier this year, and here's a link to that paper. So delving into the performance first, this is the AMD GPUs MI series, so MI25 GPUs, MI50 GPUs, and MI100 GPUs. And as you go up the ladder, you see the performance, the teraflops of the peak single precision performance going higher up to MI100 GPUs. And to go over the experimental setup of the performance that we're going to show, we utilize point-to-point and collective benchmarks from the OSU micro benchmark suite. So since the 5.7 release and the latest 5.8 release, it has ROCm extensions so that you can evaluate OSU benchmarks on AMD GPUs. So you can find that over here. And anyone who is familiar with utilizing it, so typically on NVIDIA GPUs, you would just have to pass NV2 use CUDA. Now it's NV2 use ROCm for AMD GPUs. And then usually you would pass -D CUDA to your OSU benchmark, and now you can also have support for -D ROCm. And this evaluation was done on the Corona cluster at LLNL with different partitions. So 4 MI50 AMD GPUs per node on some partitions, 4 MI60 AMD GPUs per node, and then 8 MI50 AMD GPUs per node. And our evaluation was done on the partitions with 8 MI50 AMD GPUs per node with dual socket IB HDR100 and the latest version of ROCm, which is 4.3.0. And we utilized MVAPICH GDR version 2.3.6 and the latest versions of OpenMPI and UCX, so 4.1.01 and UCX 1.11. And then we also compare against the peak achievable performance here, and we got these numbers by running the ROCm bandwidth test, which does a copy between two devices within a node to get the peak achievable bandwidth, and we also use InfiniBand per test to get the peak performance across the node. All right, and so this is intranode point-to-point performance, so that's between two GPUs within a node. We did latency, bandwidth, and bidirectional bandwidth. So for small message latency, we're able to show around 1.76 microseconds at 1 byte, which is utilizing PCI bar map memory copy. So that would be similar to what GDR copy is on the NVIDIA platform. And then for large message latency at around 4 megabytes, we have 686.95 microseconds. For bandwidth, the peak bandwidth is around 27, 28 gigabytes over here, and we're able to achieve close to 23 gigabytes using ROCm IPC, which is what's provided by the ROCm driver as well. I'm sorry, by the ROCm runtime, and then bidirectional bandwidth as well. And these were on MI50 GPUs with ROCm 4.3.0. And then we have internode point-to-point performance, so that's two GPUs each on a different node over HDR100 interconnect. So for latency, we're able to show 3.99 microseconds at 1 byte utilizing ROCm RDMA, and then 411 microseconds at 4 megabytes, and then close to peak achievable bandwidth at 256 kilobytes at around 11.6 gigabytes. And then we also evaluated different collectives. So this evaluation is done on 8 nodes with 8 GPUs per node, so a total of 64 GPUs. So for broadcast, we show around 6.63 microseconds at 4 bytes and around 1,019 microseconds at 1 megabyte. And for MPI reduce, around 3.3 microseconds at 4 bytes and around 1,500 microseconds at 1 megabyte. And then for MPI gather, so 4 microseconds at around 4 bytes and 12,935 microseconds at 1 megabyte. And for all gather, 4 microseconds at 4 bytes and 12,800 microseconds at 1 megabyte. And for MPI all reduce, we show around 16 microseconds for 4 bytes. So MPI all reduce would be more critical for a lot of high performance application workloads. And we show around 16 microseconds for 4 bytes and around 2,645 microseconds at 1 megabyte. And for all 12, around 34 microseconds for 4 bytes and around 120,000 microseconds for 1 megabyte. All right, and then to conclude this work, so as we're seeing AMD GPUs being deployed in upcoming HPC systems, it becomes more important to ensure that the ROCm-aware MPI runtime is available, and also it's optimized to, when we see that a lot of these applications are, application developers are also providing support for ROCm, and we're able to give them a ROCm-aware MPI runtime to utilize as well. So the MVAPICH 2 GDR is now ROCm-aware within the past 2 releases, and it utilizes the features that are provided by the ROCm driver in the runtime, such as ROCm IPC, RDMA, and the large bar feature. And it's available through the download website, and you can expect to continue to see optimizations in future releases. Thank you.
Yeah, Kauthar, thanks. Are there any quick questions for Kauthar?
Yeah, thanks, Kauthar. This is Adam. The gather results were interesting, where OpenMPI just kind of blew up, and then it looked like there was a pretty big spike in the MVAPICH result too. Is that?
Yeah, I actually noticed this as I was presenting, that this was tuned, so it should actually look a little better here. So yeah, we'll probably have those numbers on the MVAPICH website, but it is tuned, so it should look better than this. Yeah, that was.
I was just wondering if there was something in the system software that was causing grief, but okay, that's good to hear.
This is something that would just be resolved with tuning.
Okay, good, thanks.
Any other questions for Kauthar? If not, let's thank Kauthar again. Qinghua, would you like to share your slides and then get started?
Yeah, sure. Let me share. So can you see my screen?
Yes, yes.
Okay, so thank you, Dr. Bender, for the introduction. So hello, everyone. My name is Qinghua Zhou. So today my topic is benefits of on-the-fly compression on GPU-to-GPU communication for HPC and data science applications. So this is today's outline. So first I will introduce the motivation and the focus of this work. Then next I will briefly introduce the on-the-fly compression designs, including the compression algorithm and the framework for GPU's on-the-fly compression. Then I will look at some performance evaluation numbers. Finally, I will conclude and talk about the future work. So this is the motivation. So for HPC and data science application on modern GPU clusters, so when they run with larger problem size, they will exchange more data on the network. So this will lead to a significant increase in communication times on a larger scale. However, on modern HPC system, there's a architecture issue. For example, on the serial open power supercomputer, all the intra-node interconnection like NVLink, XBus, and PCI Gen 4 are faster than the internode interconnection infinite band EDR. So this disparity will prevent efficient scaling of applications on large GPU systems. But the CUDA-aware MPI libraries already saturate the bandwidth of IP network. So this means we need to explore other technologies to bridge the gap between internode and internode GPU communication. So compression is a popular technology to reduce the data size. Then we can take advantage of these technologies to lower the pressure on network with limited bandwidth. So these are the focus of this work. So we design on-the-fly message compression schemes in an MPI library, like MVAPICH GDR. We also optimize the existing GPU-based compression algorithm. We first implement the on-the-fly compression for point-to-point based GPU-to-GPU communication. Then for those collective operation using the point-to-point communication will also have benefits. Then we demonstrate the performance benefits for 2 kinds of applications. One is AWP ODC, which is a well-known earthquake simulation application. The other one is Desk, which is a parallel and distributed computing framework for data science. So in order to implement the on-the-fly compression, we first studied the existing lossless and the lossy compression algorithm for floating point. So because the GPU-based compression algorithm can provide a high throughput compared to the CPU-based compression algorithm, so we picked up two public compression algorithms, MPC and DFP, and they integrated them into the MVAPICH library. So we proposed a framework for the GPU-based on-the-fly compression. So in this framework, we integrate MPC and DFP and implement some optimization. So on the sender side, after compression, we got the header data and the compressed data. So and since we are focusing on the large GPU data transfer, so we use the random protocol to send the header data and the compressed data. So on the receiver side, we launched the decompression algorithm to get the original data. So this framework was published in the MUG'21 conference. You can look at detailed information in this paper. So we run the evaluation on these clusters, frontier long-haul and the liquid subsystem, and the Latency cluster. So frontier long-haul and Latency have the NVIDIA V100 GPU, and the frontier liquid has the NVIDIA RTX 5000 GPU. So this, let's first look at the Internode GPU latency. So we run the OSM macro benchmark for the optimized MPC and DFP algorithm on frontier RTX 5000 and the long-haul V100 GPU nodes. So for the MPC, it can reduce the latency up to 77.1% on RTX 5000 and 62.5% on long-haul V100 at 32 megabytes. So for the DFP, we run with different compression rate. Here, the rate means the number of bits for per floating point value. So with the lower rate, we can get higher compression ratio. So with DFP, we can reduce the latency up to 83.1% on frontier RTX and 78.3% on long-haul V100 at 32 megabytes. We also test the Internode GPU latency. So with MPC, we can reduce the latency up to 60.6% on frontier RTX at 32 megabytes. But on long-haul V100, we didn't observe performance benefit because the Internode MV link long-haul is faster than the pure MPC compression and decompression throughput. With DFP, we reduced the latency up to 79.8% on frontier RTX and 40.5% on long-haul V100 at 32 megabytes. We also run two collective operations, Mpi broadcast and Mpi gather, on some real data sets. So with the MPC, you can achieve up to 57% benefits on the dataset MSGS-PBN. For DFP opt with compression rate 4, you can achieve benefits about 85% benefits on almost all the datasets. For Mpi together, we can observe the similar trend. Now let's look at the application results. So we run the HPC application AWP on a lesson cluster. So the MPC opt can achieve up to 18% improvement for the GPU computing flops on 512 GPUs, and it reduced the runtime per time step by 15%. For the DFP opt with a compression rate 8, you can achieve up to 35% improvement of the GPU computing flops on 128 GPUs, and reduce the runtime per time step by 26%. For the data science framework desk, we run a desk benchmark. The DFP opt can achieve up to 1.56 times speed up of the throughput, and it reduce the execution time by 37% with the compression rate. Now let's conclude. So in this work, we presented on-the-fly compression techniques for optimizing GPU-to-GPU communication in an Mpi library. So we enhanced the GPU-based point-to-point communication in MVAPICH GDR with the optimized MPC and DFT compression algorithm. So at the benchmark level, the compression can can get the latency improvement for both intranode and internode communication, and also for the collective operation like MPI broadcast and MPI altogether. At the application level, the AWDC can achieve up to 18% improvement for the GPU computing flops with the MPC opt, and 35% with the DFP opt. The desk achieves up to 1.56 times speed up of the throughput and the 37% reduce runtime. So in the future, we plan to study and incorporate more GPU-based compression algorithm, and we also plan to exploit on-the-fly compression for different kinds of collective operations and also the DL applications. So that's all. Thank you.
Thanks, Tsinghua. Are there any quick questions for Tsinghua?
I'll have one, of course. So,
sure, go ahead.
yeah, it's like somebody gave me the mic.
Yeah, go ahead. Yeah.
You always have the mic.
That's right. Yeah, I missed it. Are any of the results including lossy compression, or is it all lossless?
We have the results for both lossy and lossless.
So, Adam, while Tsinghua brings up the slides, MPC is lossless and ZFP is lossless.
MPC, yeah, let me go back to this slide. So MPC is the lossless and ZFP is lossy.
Yeah, I think ZFP, it has a mode where you can run it in lossless, right? I think. So you were actually using lossy for this work?
Yeah, so for the GPU version, so as far as I know, so the GPU version provides the lossy compression, right?
Oh yeah, I'm not sure. I thought it had a mode you could.
Yeah, maybe for the CPU based, it may support the lossless compression. But here we only use the GPU compression, so we use the lossy compression.
Okay.
Yeah.
Yeah. So then that always leads to the next question of like, does it affect the application outcome? And have you looked at that?
Short answer is no, it does not. So we checked with the developer of AWP ODC to make sure that let's say the accuracy is as expected and the application is converging, and they confirmed that the application is indeed converging. So I think this kind of goes back to a misconception with a lot of HPC folks saying that they probably need accuracy to the like 100th decimal place. Probably most applications don't need that, something which we are seeing on the deep learning front. So this may be alluding to that.
Yep. Yeah, I think it's really interesting work. Very nice work. Yeah, we had wondered about that too, coming from the checkpointing side, where we started looking at using lossy compression and checkpoints, and then restarting from those and trying to figure out if you end up at the same result or not, right? And it's a tough question. You have to sort of involve the application developers to figure out if the answer you're getting is still valid.
Definitely. And here we played around with a lot of compression ratios. So you will see that we have like a few compression ratios in the slide. If you increase that beyond like whatever is mentioned in the slide, we do see validation errors. So yes, making the data too small, being like overly greedy does result in validation issues. So you have to strike that right value.
Yeah, that's good. And I also missed it. Are you applying this yet to like all reduce and deep learning applications, or?
That's a very good question, Tsinghua.
Yeah, so currently we are looking at the some DL applications to try the compression design. So that's our future work.
So currently Tsinghua is looking at a couple of dense collectives like all-to-all and all-gather. All-reduce is also on our roadmap. So deep learning definitely is on our crosshairs because of the sheer volume of data it communicates.
Yep. Yeah, okay, thanks guys.
And yes, checkpointing or MPI IO, all of those things can also be like any data, like any operation, any communication operation that transfers large volumes of data, like IO, checkpoint, like deep learning, everything can potentially benefit from this approach.
Yeah, and Adam, in my talk, I showed some initial numbers for all to all. You can take a look at that. And we are working on the other collectives.
Okay.
Chingwa, there is a question on the Q&A. Do we use MPC for header due to lossless?
No, we are not just using header for lossless, because the header data will contain some like control parameter for both MPC and ZLP. We use this header information to send out some necessary message to let the receiver to know some key information. Yeah, that's why we use header data.
There is a second question also, follow-up question.
Yeah, so currently we provide the runtime parameter to let the user to choose the algorithm. Currently we support MPC and ZLP. They can use runtime parameter to turn on one of these conversion algorithms.
Okay, so thanks again, Chingwa. I think to keep track on the schedule, so let's move to the next talk. Thank you, Chingwa. Tenchun, you are next. Can you please share your slides and get started?
I'm sharing. Do you see my screen?
No.
About this?
Yes.
Okay. Okay, thank you for the introduction from Dr. Penda. Hi, my name is Chen Chun, and I'm currently working on the MVAPICH 2 GDR project. And today I would like to discuss the work I've been doing with the team to optimize the performance of MVAPICH 2 GDR on DGX A100 system. So the focus of the talk is the performance of MVAPICH GDR on DGX A100. And for here, it's a brief introduction leading into the talk. And with the advent of the NVIDIA DGX A100 system, MVAPICH 2 GDR 56, which you can download now from the website as the most recent release before month, includes optimized support for point-to-point and collective communication. So if you were here in Harris' tutorial, we discussed that we are fully support DGX systems from this release, and I will discuss more in the following talk. To start, this is the image shows that the topology of NVIDIA DGX A100 node. As you can see, there are two CPUs in two sockets, and each socket contains two PCIe switches, and each PCIe switch connects with two MANETs MIC. However, the most novel design in this system is that it includes eight GPU switch are connected with a V switch. You can imagine that this new architecture will lead to very low latency between GPUs and even between nodes. So we are very excited to optimize MVAPICH 2 GDR for the new system. And so far, we have got some good performance numbers, and I will share with you in the following slides. Before that, let's look into the cluster we tested. We used the GPU cluster as our testbed. Instead of GPU, there are 24 NVIDIA DGX A100 nodes. And for each node, there are 8 NVIDIA A100 Tensor Core GPUs and 2 AMD ROM CPUs with 1 terabyte memory. And the nodes are connected with MANETs HDR200 switches. And the OS is Ubuntu 20, and the CUDA version we use is 11.0. And the NICO version is 2.8.4. The MVAPICH 2 GDR version is the latest release, 236. And from this release, we also support MVAPICH 2 GDR plus NICO hybrid feature. As to say, if users have pre-installed NICO in their system, MVAPICH 2 GDR will load the NICO library automatically and enable some features with MVAPICH 2 GDR. Another feature regarding to NICO is that OSU macro benchmarks has NICO benchmark support from the latest release 5.8. So far, we support NICO-based point-to-point benchmarks such as latency, bandwidth, and by bandwidth, and also some collectives such as Altogether, or reduce, broadcast, reduce, and reduce scatter. And we will also compare the performance numbers using this new benchmark in the following slides. So first, let's see the performance of Altogether on Zeta GPU. We show the performance numbers for 2 and 4 nodes. This is 2 nodes, it is 4 nodes. And remember, each node contains 8 GPUs, so we have 16 and 32 GPUs for the 2 figures. And basically, for the small messages, our 2 MVAPICH GDR performs well compared to NICO. For example, in the 2 node figure, we have 2.3 times improvement for 60 bytes here, and even 1 times improvement for 4 nodes. For large messages, our tuned MVAPICH GDR is competitive with NICO. And we have the similar numbers for broadcast. For 2 node case, we have 1 time improvement at 16 kilobytes. And for 4 node case, we have even 5 times improvement at 16 kilobytes. And we also have competitive performance for large messages here. For reduce, we have even 4.6 times improvement at 16 gigabytes for 4 nodes. It shows that our kernel-based implementation of reduce also performs well on the new DGX system. And MPI reduce is widely used in deep learning. As you can see, we also performs well for small messages. There are 2.5 improvement for 4 nodes and 4 kilobytes. And also, we also have the competitive performance for large message here. And that's all about the performance number I would like to show. And so let's move on to conclusion. So in the recent work, we optimized the performance of GPU-based collective communication and support for NVIDIA DGX A100 systems. And we fully support the new system and specifically enhance several collective tuning such as Altogether, broadcast, reduce, and all-reduce. And for small messages, we performed well. We have up to 5 times improvement compared to NICO. And for large messages, MVAPICH GDR is also competitive with the baseline. And now the tuning for DGX A100 system is available from the latest release of MVAPICH GDR 2.6, and we will keep optimizing it in the future releases. And in the future, we also plan to enhance the tuning for more collectives. And that's all about my presentation. Thank you.
Thanks, Chenchun. Are there any questions for Chenchun?
I have a quick question. Do you expect more collectives support to come, or like more optimizations to come in the future?
Yes. Now we are always on our roadmap, and we are going to have a plan like other collectives for like gather, scatter.
Okay, sure. Thanks.
There is a question on the QA. The improvement is on the smaller messages. Yes. Any other questions from anybody else? Okay, so if not, let's thank again Chenchun. So let's go to the second set of presenters. Let me quickly introduce them. I think you can see my slides.
Yes, Dr. Banda.
Yeah. So the next set of presentations will be done by Sule, Bharat, and Kausik. So Sule is a 4th-year PhD student in the MVAPICH team. His research include high-performance computing, shared memory communication, and Mpi libraries on high-performance cloud systems. So he will be presenting performance studies of MVAPICH libraries on the AWS and Oracle clouds. Once again, in today morning, I showed some initial results, and he will go into more details. After that, Bharat will be presenting benefits of streaming aggregation with SAR V2 in MVAPICH 2. He's a fourth-year PhD student in the MVAPICH team, and his research interests include high-performance computing, architecture-aware communication, network hardware-based offloading, and topology-aware collective algorithms. I also showed some initial results from the streaming aggregation in the morning talk. Bharat will expand on that. And finally, Kausik will be presenting optimizing communication performance of derived data types in MVAPICH 2. He's a fourth-year PhD student. His research interests again include high-performance computing, computer architecture, and parallel programming. He's also a member of the MVAPICH team, and I showed some initial one slide. I think he will expand more. So with that introduction, so let's get started. Sule, if you can share your presentation and get started.
Sure. So let me see. So is this visible to everyone?
Yes, Shule.
Okay. So hi everyone, I'm Shule Xu from the MVAPICH group. So today, thank Dr. Brenner introduced me, and today I'm going to report our recent achievements of the performance studies of MVAPICH 2 libraries on HPC cloud systems like AWS or Oracle OCI HPC cloud. So recently, with the development of cloud computing and virtualization technologies, high performance cloud service is becoming a more popular choice for many HPC users. Comparing to the traditional supercomputing centers, high performance cloud systems usually are more flexible, accessible, and also cost effective. Users of HPC clouds usually have more freedom to control the whole running environment, like software stacks, depending libraries, or the operating system kernel modules. So our group are making efforts to explore the MPI performance characteristics and explore the possible optimization methods on those different cloud systems with different architectures and hardware and software configurations. And in this short presentation, I will introduce some of our recent achievements on AWS and the Oracle OCI HPC clouds since last month. And first is our optimization work on AWS. And as Matt introduced, currently our MVAPICH 2X AWS released version based on the Elastic Fabric adapter on AWS EC2. And we have support to any x86 instance types that support the EFA. And just as Matt introduced recently, they released the new ARM architecture with their customized AWS Graviton ARM CPU. So we bring our previous optimizations, including utilizing larger MTU size of scalable, reliable datagram, and also reordering data packets since the scalable since SRD has some auto-order package issue on receiver side. And we also bring our performance tuning and have a new dedicated performance tuning and algorithm selection based on the new ARM system. And since the users of AWS clouds has freedom to load their kernel modules like GDR or XPMM, we have automatic XPMM module detection in our MVAPICH 2X AWS version. And we also did a performance evaluation based on our optimized MVAPICH 2X AWS and comparing it to the built-in OpenMPI modules of their parallel cluster default image. And in the experiment, we use C6GN.16X large with 64 cores, one socket and 64 cores on each node. And the operating system is Amazon Linux 2. The parallel cluster version is 2.7.1, which is their latest version. And we use the OSU micro benchmark 5.8 as our benchmark. So here is the point-to-point performance. of Internode tests. We can see that due to the special characteristics of elastic fabric adapter, unlike the InfiniBand or Rocky V2, it has higher baseline point-to-point latency, and both the verbs level and MPI level baseline latency is about 15 microseconds, and it depends on the allocation. So for some allocation, it got higher latency, and in our previous observation, we observe up to 20 microseconds in some of the allocation. But for the performance comparison between two MPI libraries, we found they have close latency performance. But for small messages less than 1 kilobyte and larger messages larger than 1 megabyte, we found that since the MVAPICH directly call the verb score and OpenMPI use leaf fabric, there's some performance difference, and we observe MVAPICH AWS has about 12% lower latency for small and the large message sizes messages. And we also did a collective performance evaluation on up to 32 C6G instances, which is the largest allocation we currently have. And here is some of the results. Sorry. In our all-reduced test with 32 nodes and 64 processes per node, we observe up to 2 times lower latency in small and medium messages. And in the scatter test with 32 nodes and 64 processes per node, we observe up to 3 times lower latency in the medium. And that's the most thing we already have for the optimization work on the AWS ARM system. And similarly, we also started our collaboration work since last year with Oracle High Performance Cloud team, and we bring our support to our MVAPICH and MVAPICH libraries to Oracle High Performance Cloud system. So our current performance optimization on Oracle High Performance Cloud system is based on their bare metal HPC2 instance shape and their Oracle Linux 7 operating system with their own platform HPC image. We have dedicated performance tuning for both the point-to-point communication pattern and the collective communication patterns. And similar to other high-performance cloud system, users on Oracle high-performance system has control of the operating system kernel modules. So we also have automatic XBMM kernel module detection on this system. And for the experiment setups, we use the bare metal HPC 2.36. I believe for now this is the only one that support 100 Gbps bandwidth Rocky V2 on their system, and we also we also use their cluster network to build the network with version 2.6.3, and so the versions of MPI libraries we used for evaluation is our latest MVAPICH X 2.3, and their built-in HPCX module with version 2.8.1, and the latest Intel MPI 2021, which get from their latest one API on their official website. So first is the point-to-point internode latency. For Oracle system, we evaluated small message internode latency and large message internode bandwidth. The performance of those two MPI libraries is very close, except that there's some performance difference in the medium medium message size of 256 bytes, and in the large message, in the medium and large message bandwidth, we observe up to 1.9 times higher bandwidth of MIPICH2X library on some medium messages comparing to Intel Mpi 2021. And we also did the collective test for up to 8 BMHPC2 instances, which is also the largest allocation we can have on Oracle systems. So comparing to other two MPI libraries, we observe some difference in large messages about 1 megabyte. We have 2.7 lower latency comparing to Intel MPI in MIPICH2X. And in the reduced test with 32 process per node and 8 nodes, we observe about 21 times lower latency for very small messages of 4 bytes of MIPICH2X comparing to other MPI library, which is HPCX and Intel MPI. We also did the application level tests on Oracle system using the mini-MR. And in small messages, we observe close performance of 3 in MPI libraries, but when the size grow up to 8 nodes, the MIPICH2 shows better scalability, and we find 4 times lower execution time comparing to Intel MPI on 8 node scale in this application. So this is some of the achievements we have for those two cloud systems, and we also have a lot of work in progress and some future plans. On AWS, we are looking for some further optimization on larger scale collectives, especially for broadcast communication pattern. And we also have a new design based on the new RDMA read feature, and the GDR on their specific P4D instances is nearly finished. And for Oracle system, we are looking for further performance optimization for other instance shapes. And we are working closely with their HPC team to have more user-friendly deployment for the MFPICH2 MPI library stacks. And that's the most thing I have. Is there any questions?
Sule, thanks. Are there any questions for Sule? Okay. If not, let's thank again Sule. We'll move to the last 2 presentations of today's. So Bharat, if you'd like to get started.
Yeah, I hope you can see me, hear me, and see the slides.
Yes, yes.
Okay, just a second, it's hanging. Okay, thank you, Dr. Panda, for the introduction. So, hi everyone, I'm Bharat. I'm a PhD student in the MVAPICH group, and I primarily work on collective optimizations. So today I'll be presenting the benefits of streaming aggregation with Sharp v2 in the MVAPICH2 or the MVAPICH2X library. So the presentation is relatively short, and I'll try to keep it short in the interest of time. So I will be presenting an intro or a background on what Sharp is and all the technologies they have. And I will then move on to a performance evaluation for MPI all reduce and MPI reduce, which are the 2 most popular reduction collectives. And then I'll move on to a summary of what benefits we see in general. So in general, we observe this a lot, that there are MPI collectives that use aggregation, and they're significant to the total runtime of the application. So some examples would be Milk or applications like that, which use large message MPI all reduce. And there are also applications which use small message, but they do not occupy as much of the application time as the ones which use large messages. So when designing an MPI library, we kind of have an ideal set of goals. to achieve good performance with collectives. So the first and foremost is overlap of computation and communication. So this is useful when you have multiple processes on a node, and you kind of have to communicate and also do stuff in parallel where you can compute so that there are no bottlenecks in the system. So this ties in to using offloading protocols and things like that. So Sharp is one of them. The second goal is to maximally utilize CPU resources. So what this means is that the CPU should do useful tasks and not like it shouldn't stay idle and should only perform useful tasks. The third goal is scale out and scale up efficiency. So we need a combination of good intranode algorithms as well as very efficient internode algorithms. And of course, no one likes to change application code to get better performance. So we should try to tune stuff and let the user run what they usually run, and they give them better performance. And the last goal is to utilize high levels of parallelism. So this is similar to utilizing CPU resources, where we can we can do things like splitting up computation between cores and using OpenMP threads and things like that. So in general, co-designing software and hardware elements for the best results is the way to go. So what I mean by that is using writing efficient code along with using good hardware APIs and technologies that are available. So this ties into Sharp. So Sharp is a scalable hierarchical aggregation and reduction protocol. So the name is kind of descriptive on its own. So it's essentially it essentially aggregates results and then does reductions and then distributes the results. So it's a framework for that. And there is support at the switch level as well as the HCA, and then there are a bunch of APIs that they provide for MPI libraries. So the advantages are it offloads computation and communication, has very low latency for small messages. They also recently introduced streaming aggregation, which guarantees like maximum bandwidth utilization while also guaranteeing the lowest latency possible. So they have two concepts, hierarchical tree and streaming aggregation. So I will explain them briefly. So these images are taken from their paper, and I've linked it like below the slide. So on the left side, you see aggregation trees. So the red and cyan colors are two groups. So you can imagine those as communicators. And what we kind of try to achieve is we try to offload the all-reduce operation to the network. And then there are aggregation nodes which kind of gather the results, do compute on the fly, and then distribute the results. So all this happens at wire rate. And as you can see from the tree, it reduces the amount of duplicate messages that are sent. And there are a lot of optimizations that they do behind the hood. So one of them is on the right side, where you see a switch level reduction. So what they have implemented for streaming aggregation is a pipelined ring-based algorithm between these combiners. So as packets arrive, MTU-sized packets arrive, they compute and they get the result on the fly, and then it goes to a combiner called an FCU, which is a collective unit which can just give the reduced result out of the net, like send the reduced result out of the network. So coming to the results, we've kind of we're presenting basic results on 4 nodes and 16 nodes on a platform with Intel Gold 6138 with a dual socket CPU and HDR200. So I think we use Sharp 2.3 with the version that comes with HPCX 2.9. As you can see on the left and right graphs, we present results from 16K all the way to 16M. So because of the scale on the y-axis, it looks like there are no benefits for 16K, but then you will see 3x benefits across the board, like all the way from 16K to 16M for 1 ppm jobs. And the reason HPCX isn't visible here is because our newer version of MVAPICH 2 is equal to that, so they're overlapping with each other. So basically, we've made some optimizations to caching and using streaming aggregation at the right time. And that is why we have 3x improvement over the previous version of MVAPICH, which also supported Sharp. So coming to MPI reduce, we see an 8.5x and 15.6x benefits respectively on 4 and 16 nodes. And again, so Sharp provides flat scalability. If you observe the latency numbers for MVAPICH 2x next, you'll see that this almost the same on 4 nodes as well as 16 nodes. And we've seen in the past that it actually scales, has flat scaling all the way up to 7,000 nodes. So we have not done any large scale studies with streaming aggregation yet, but that's like future work. The reason why we see more benefits for reductions is because our host-based algorithms for larger messages are less efficient when compared to Sharp-based all reduce. So again, Sharp primitives are not used for MPI reduce as of yet. They don't support it at the API level. So what we did was we perform an MPI all reduce and ignore the receive buff and all the other processes. So that essentially performs a reduction. So coming to the conclusion, pure software-based schemes are limiting, and you will see like an exponential scaling as the message size and scale increases. And Sharp is highly effective with good latency and scalability, and with flat scaling, even with streaming aggregation. And they do all of this with at wire rate and with optimal bandwidth numbers. So this is why it's a technology that's really impressive. So in terms of future work, we plan to do some comprehensive evaluation of benchmarks and applications at large scales, and then some scaling studies with larger number of processes per node, maybe even better designs with more processes per node. And we also plan to optimize some non-blocking collectives to use streaming aggregation and hopefully come up with novel and better designs in the process. So that's about it. If you have any questions, feel free to ask me or email me.
Yeah, Bharat, thanks. Are there any questions for Bharat?
Yeah, I think there is.
These questions were for Sule, I believe.
Oh, was it?
I believe
Yeah, that was the initial list. But yeah, hi, Roth. Yeah, nice talk. So have you guys plugged in, can you use this now in deep learning? Like, can you run Horovod on top of there and take advantage of it?
Yeah, so we haven't evaluated that yet, but that is something on our roadmap. So we definitely plan to run more applications, especially deep learning. And we also plan to support GPU buffers. So Sharp has GPU direct RDMA support. So we plan to do some evaluations with that as well and see how it turns out.
Okay. And I noticed in your results, it looked like they were all one process per node. Does, are there any problems with using multiple processes per node, or I guess you could just do a host-based reduction before you launch the network piece?
Yeah, so there's a couple of problems. One, so there's a limit on the number of execution contexts you can have with Sharp. So that's per node. So as you increase the number of processes, it doesn't let you initialize Sharp resources. So they have restrictions at the HC and the switch level. So that's the first thing. And the second thing is we need to design better algorithms to utilize inter and intranode to use the internode component of Sharp because a two-level algorithm is going to be inefficient, right? With the reduction and then an all reduce and then a broadcast.
Yeah.
So yeah, so that's also in our roadmap, trying to come up with newer designs. But it's a non-trivial problem as of now, mainly because there are resource limitations with what Sharp can do.
Okay. Okay, thanks.
So thanks, Bharat. Then let's go to Kausix Presentations. The last one for today, Kausik.
Can you guys see my screen?
Yeah, yeah. You need to have the presentation mode. Yeah.
So thanks, Dr. Panda, for the introduction. Hi, everyone. I'm Kaushik. I'm going to be talking about the optimizations that we did in our MVAPICH for MPI derived data types. So this is the outline. First, I'm going to briefly introduce you to what MPI derived data types are, and then I'll talk about the problem statement, like the current issue, and then I'll jump to the evaluation section, where I'll show some benchmark numbers and mini app numbers, and finally I'll conclude. So as we all know that MPI's distributed memory programming model, MPI provides this abstraction of rank where processes communicate each other using primitives like sends, receives, and other collective primitives. And all these primitives take in MPI data type and count and size as their argument. So MPI data type here is used to let MPI know about the layout of the data that user wants to basically transfer to other processes. So it can be a simple intrinsic data type like int, double, or float and whatnot, and a more complicated data types like type vector, type index, and type config, and so on. So derived data types are used to represent more complex layout that cannot be represented using your simple int and doubles and floats. So these are the example of some layouts where derived data types come in handy. So on my screen, first you see the example of a data layout for 2D stencil exchange. Here, if you see all the boxes in my row, they are contiguous in memory, assuming a row major order, and the column may not be contiguous in memory. So if a process wants to exchange this column to a nearby process, it either needs to have multiple isents or the other option is to pack. But MPI conveniently provides something called derived data types, where you can, using that, you can represent this entire column, and then you can use a single isent to transfer the data. So this is useful both in terms of programming advantage, and also it transfers the onus of optimizing derived data types to the application or to the MPI implementers. And the second example is the NAS LU. This is again a 3D grid exchange where you see a bunch of edges are being exchanged, which again may not be contiguous in memory. So these are two examples of some non-contiguous layouts that exist. So this is like a quick background of different data types, APIs that MPI provides. The first one on the top left is MPI type config. This is just a bunch of ints or chars or floats or whatnot. You can just combine them and just represent as a single unit. The second one right below that is type vector. This is like a regular data type with a fixed block length and a fixed stride, where block is the amount of data that the contiguous portion holds, and stride is the distance between two segments. And the next is type index, which can have blocks of different lengths. And the fourth one is type struct, where each block in turn can have different primitive data types. Like the first one can have int, this one can have float, and each one can have any type of data type. And this is a simple example showing like nested data types, which contains multiple levels of data types. So now moving on, MPI libraries typically have two types of schemes for MPI derived data types based transfer. First one is the hardware assisted, and the next one is the host-based scheme. So in hardware assisted scheme, MPI libraries typically flatten the given MPI layout. So this is the memory layout that is given to the MPI library. It flattens to get the list of memory addresses and the lengths. Once that is obtained, MPI libraries register the IOVs, and then it can use hardware assisted primitives to directly post all the IOVs using a single call, where the HCA gathers these from different memory locations at the source side, and it can scatter it at the destination site. And the second approach is for the library to pack everything into a single contiguous memory and then post it. So these are the two approaches. Now moving on to the problem. So now that we have seen there are two different ways to transfer, and we have seen that any type of memory layout can exist, the performance of a DDT transfer scheme depends on the type of scheme that you use, and it also depends on your memory layout. One way to classify them is based on the amount of the block length to stride ratio, which is which will tell us how sparse or dense the layout is. And another thing is how many times the same layout is getting reused again and again. This will in turn, if the frequency is more, it will help the libraries amortize the cost, and more optimizations are possible. So we have designed a scheme taking all of these things into account, and next I'll show you some of the results which are with our proposed scheme. So for the experiments that we did, this is the platform that we used, and we have compared MVAPICH to X, OpenMPI, and Intel MPI libraries, and we used OMB with vector bench DDT support, and DDT bench, which is like a standard benchmark which has all the layouts used by popular HPC applications, and MiniGhost mini app. So these are the three benchmarks and applications that we ran. So this is the result of a vector benchmark. So here we are basically transferring a vector of block length 4 KB and stride 8 KB in a ping pong fashion. And for this simple layout, we see that the proposed scheme gives up to 30% improvement over OpenMPI and 2x improvement over Intel MPI. And the x-axis, the x-axis we see the number of segments varying. So we see that as the segments increases, the benefits are much more. So now I'm going to show you the performance of DDT bench. So DDT bench, like I told you, has a bunch of suits, application suits, where each application suit uses the actual layout that's used by that application. So for example, on the left side of my screen, you see NAS-MG. So this benchmark uses the layout that is used by the NAS-MG application. So NAS-MG is again has a grid where it has one type of layout in the X direction and another type of layout in the Y direction. So I've mentioned that here, and that basically changes based on the input. The exact numbers change based on the input. And for NAS-MG, we see up to 28% improvement over MVAPICH and 2.5x over Intel MPI. So here, these two applications, the common thing is there is a variability in the layout, memory layout itself, where you see 8 bytes block length on one direction and 5 KB block length in another direction. Similarly, even for WRF. So this is typically common with a lot of applications where you have different types of layouts, and that's where our scheme comes and tries to give the best performance considering what's best for both of them. So finally, I'm going to be showing this this mini application number. So we ran mini ghost with 1 ppn up to 128 nodes. These are pure internode numbers, and here we show the total execution time, which includes the compute and communication time, and the compute doesn't change with the experiment. Only the the compute doesn't change as we increase the node. Only the communication changes, and this is a modified version of MiniGhost which has MPI DDT support to it. Here again, we see that even at 128 nodes, we see up to like 35% with Intel MPI and around 8 to 9% with other MPI libraries in the total runtime. So to conclude, DDT cost is impacted by transfer schemes, layouts, and the DDT operation. So we take all of these into account to propose a dynamic scheme, and we show improvements both at the micro benchmark level and at the mini ghost application level as well. In future, we are planning to do more studies and see if we can extend it to other accelerators as well. Thank you.
Thanks, Kausik. Are there any questions for Kausik?
Is there any plan to look at the GPU side of things and also look at things like UMR?
Yeah, yes. We are currently exploring that, both the GPU side and UMR in the GPU side. Yeah, we are exploring.
Do you have any thoughts on which would be better, the user mode memory registration or SGL? Any thoughts on pros and cons?
Yeah, so in SGL, the main disadvantage I would say is you need an additional QP. So if you want to use SGL, you have to add support for DCT, dynamic scalable transport. In UMR, you don't have that issue, but in UMR, you have to come up with a way to exchange the entire layout's address. Since it's an RDMA thing, you need to know everybody else's address, which is not the case for SGL. So the layout exchange part is minimum there, but in UMR, you need to exchange layout. Yeah.
Okay, thank you.
Are there questions from anybody else for any of the speakers? Okay, so I think if not, then let's call it a day.